Hey everybody, I'm back with a little demo on minerals. I have so many cool mineral samples. I wish I could show them all to you and you could be right here in the lab with me, but we have to do it online, as you know, so that's okay. But I want to show you some really cool things just to kind of get you a little excited about minerals. So I love minerals, but anyway, I have a few things for you to see today. First thing I wanted to show you is actually fool's gold. And you've probably seen fool's gold before, but probably never like this. So this cube that you see here, so shiny. Look at this. You can actually see my laptop. Can you see the reflection of the laptop in there? So probably you could see yourself in it. Whoa, look at that. Okay, so, well, you see the camera. But anyway, this is actually fool's gold. Nobody made this. Nobody cut it. Nobody polished it. It 100% forms this way naturally in nature. So that's what a perfect crystal of fool's gold looks like. And you can see something about it that's really cool. It has perfect 90-degree angles. Really, really neat. Here's a bigger one. It's just not as nice because it's a little not as shiny, and also has this broken edge, but it's kind of a bigger crystal. So anyway, this is a crystal. And a crystal is a mineral sample that is actually bound by crystal faces, like this one is. So you have the beautiful crystal faces, but that's a crystal. So maybe not exactly the shape that you're used to when you think of a crystal, but this is a crystal. This is just kind of neat. I don't know if this will show up at all on the camera, but this is bornite, which is called peacock ore. Very, very beautiful. Has this kind of iridescent purplish sheen on it. So I wanted to show you that too. Now, another very important mineral in the crust is something called calcite, very common mineral. Now, calcite, I'm going to get you some little samples of calcite here. One thing that I want to show you about calcite, and I'm actually going to turn kind of the camera a little bit like this. This is a calcite sample, but I want to show you something very special about this. I'm kind of wondering, I hope this shows up on the camera okay, but I'm going to show you something special about this. I've got so much glare here, waiting for the camera to kind of adjust itself. But I wonder if it'd be better to go like this and kind of turn this down, maybe like that. I don't know. Maybe not. Okay, it's all right. But what I have right here is some, wait for the glare to go away, that's 10% HCl. It's hydrochloric acid. It's not the kind of stuff you want to get on your skin, but I'm going to show you what happens if I put some HCl on this calcite sample. Okay, here it goes. I'm going to show you, and hopefully this shows up. Here, I'm going to put it next to the microphone. Can you hear that? It's actually fizzing. So I don't know if you can see that. Maybe you can, maybe you can't. But anyway, the HCl is reacting vigorously with the calcite. Something that's kind of cool is that little seashells and a lot of marine animals actually make their shells out of calcite. So if I take this shell right here and I put some HCl on it, you hear it fizzing? So it's actually fizzing. You can actually see the vapor of CO2 coming up off of it. Okay. I don't know if you can see that okay, but anyway, it's this is maybe even better. This is actually just calcite sand. I'll kind of do it like this so you can see this. But can you see it effervescing and bubbling and stuff, right? So anyway, that's the reaction of acid with calcite. So a lot of marine creatures actually make their shells out of calcite. Calcite has a lot of other really cool features. I wanted to show this to you too. So here is some very, very clear calcite. And I'm going to show you the box right here, okay? So you can read that optical calcite Iceland spar. Some people call this Viking stone or Viking sunstone. I want you to take a look at what you see now if you try to read the same letters through the calcite. And if you take a look, you'll notice that there's actually double. You're seeing double now, right? Y'all see that? So something really cool that calcite does, besides being reactive with acid, is it actually splits light waves. And this, by the way, is how polarized sunglasses, polarized lenses, other polarized things work. It actually has little crystals of, maybe not calcite, but something like calcite that splits light waves. So that is calcite. There's another really cool rock here I want to show you. That's called ulexite. Ulexite. Yes, ulexite. So this is what ulexite looks like. It's called TV stone. And the reason that it's called TV stone is if I take this, remember we had our optical calcite, right? Oh, actually, this isn't going to show up. But I'm going to see if you can see this on the camera. I'm going to put a piece of paper up to the surface of this and just watch what happens. So it actually will project it onto the surface. And I don't know, hopefully that looks kind of cool on camera. And when you're in person, it certainly does look cool. But I just wanted to show that to you too. The last thing I want to show you is this. This is called lodestone or magnetite, and it is magnetic. And if I pitch this down so you can see our little compass right here, you can see that this is highly magnetic and messes with the compass. So just showing you some of the interesting properties of minerals. Okay, well, just wanted to show you those, so I'll switch you over to the lecture now. Thank you for paying attention. Hello everybody, I hope you enjoyed that little demonstration about minerals, and wish so bad that I could meet you all and show you some of these things in person, but that's the way it is with online classes. So anyway, we're going to continue along our lecture for minerals, and do hope you enjoyed this one. This is one of my favorites, but I'll try not to go on too long, because you know how it is with subjects you enjoy, you just sometimes go on a bit too long. But I'll try to keep it short and sweet with the information that you need. And speaking of the information you need, I hope you have your lecture assignment number 6 right here in front of you. So this is on minerals, and this is kind of a cool picture in the front. If you just didn't see that guy right there, right, and this guy right, whoops, my pen's going flying. This guy right here, you probably would just think that's like a close-up of some mineral, but it's actually a real cave in Chihuahua, Mexico. And you can go and actually see crystals this big. Pretty amazing, huh? So those are gypsum crystals, and we'll talk a little bit more about gypsum as we go along. So, minerals tell us so many things. They tell us the composition of the rocks. They tell us how the rocks formed. They tell us, for example, the pressure and the temperature conditions that they formed under. They can tell us if they have been modified, or whether the rock's been modified by metamorphism. We're going to see lots of examples of that when we talk about metamorphism in this class. But anyway, they tell us so much stuff. So, even whether there's been meteorite impacts, because certain minerals are only found in meteorites. So we can look at things like that too. So many things, and you'll see as we move along in this class how much minerals can tell us. Now, there are 5 criteria that define a mineral. So you need to know, first of all, what the heck is a mineral, right? That's the first thing you need to know. So a mineral depends on 5 things. First of all, they have to be naturally occurring. So this nice big 69-carat diamond from Murfreesboro, Arkansas, one of the few places in America where you can find diamonds, real natural diamonds. And by the way, if you're ever going through Arkansas, you can stop there and dig for diamonds all by yourself, and people find them. It's kind of interesting. I've never done it, but I know a lot of people that have. So anyway, sometimes you get lucky. You can find big diamonds like that. But these synthetic blue sapphires you see up there, we don't call that a mineral because it's synthetic. So it's made by man. Second, the mineral has to be formed by some kind of geologic process. Okay. Now we're going to segue right now into I'm trying to get all these, so many wires and stuff around me. We're going to segue right now into a question number 2. We talk about different ways that minerals are made. So it has to be formed by a geologic process. So let me give you 5 examples of geologic processes that form minerals. Okay. So one way is to precipitate out of water. So you kind of saw in the previous demonstration when I did matter, remember I poured those 2 liquids together and it made a precipitate, a yellow precipitate. Same principle, right? Sometimes when waters with different minerals react, those minerals can precipitate out of the water. You probably know that minerals can be dissolved in water, right? And they can precipitate out. And that's one way of forming rocks. So these are real famous tufa towers in Mono Lake, California. Those formed by underwater hydrothermal vents. And they build up these tufa towers made of calcium carbonate. So that's one way. So you could also have evaporation, precipitation. So that's one way you could have it. You could have crystallization from a melt. So imagine, a hot volcano spurting out lava. The lava cools and crystallizes. That's another way. You could have freezing of a gas. Now that's relatively rare, but it does happen. Okay. So for example, you can see that all this sulfur gas is freezing onto the surface and forming that yellow sulfur near a volcanic vent in Italy. Another way is from pressure, just growth at high pressure. One thing that's kind of cool, and I kid you not, this is real. You can take peanut butter or any kind of organic material that contains carbon, and if you put it under sufficient pressure, you can make a diamond. It's true. What's diamond made out of? Carbon, right? So is peanut butter mineral? No, it's not a mineral. But if you put it under enough pressure, you can make a mineral. Okay, so that's another way that we can make minerals. Another important way is what's called mineralization or biomineralization. This is when atom by atom, maybe living tissues are replaced with, well, I shouldn't say living tissues, dead tissues or biological tissues, or it could just be any kind of matter that's not a mineral, gets replaced with mineral, just atom by atom, molecule by molecule, gets replaced by mineral content. And so that's how, for example, fossils are made, right? So those bones of dinosaurs that you see at the museum, those are not real bone tissue anymore. It's not like the bones in your body, right? These bones have been replaced by rock, by mineral, okay? That's a mineralization process or biomineralization, okay? So those are the 5 ways. Back to question number 1. What's another criterion that we need to be a mineral? Well, you need to be solid. So for example, believe it or not, we actually consider glacial ice to be a mineral, but of course we don't consider the water that forms the glacial ice to be a mineral. Why? Because minerals have to be solid. Now, very, very important aspect of minerals that a little bit harder to understand is they have to have a crystal structure. So what does a crystal structure mean? Well, it means that every atom in the mineral, every atom has a place, and there's a place for every atom. So if you look at this mineral structure of halite, which is rock salt, you can see that it goes purple, green, purple, green, purple, green, purple, green. Okay? You notice that there's a pattern. Okay? Minerals form in a pattern, and you can see that pattern actually played out in the macroscopic hand sample of whatever mineral, like quartz, or some of the minerals that I showed you in the beginning of this lecture in the demo, right? Remember that perfect cube of pyrite fool's gold, right? Why does it happen like that? It's because it has that crystal structure, and it plays out even macroscopically. That means you can see with your hand, see with your eyes, hold in your hand. So that's the crystal structure. Every atom has a place, and there's a place for every atom in a mineral. Okay. The last thing is that minerals have to be definable, have to have a definable chemical formula. So you have to be able to define its chemical composition with a formula. So for example, galena, PbS, lead sulfide, okay? Halite, sodium chloride, right? Quartz, silicon, SiO2, right? Silicon dioxide. So all these things, you're able to write a chemical formula that generalizes its chemical composition. You can't do that for like a human. You can't write the chemical formula of a human. Okay, it's because we have differing amounts of different elements and blah blah blah. So you can't do that for, I don't know, wood or a tree or a person or plastic or whatever else. Okay, but minerals you can. Okay, every quartz crystal is made out of SiO2. No exceptions. All right, so let's do some practice. What do y'all think? Mineral or not? Is glass a mineral? Well, no. Why isn't it a mineral? Few reasons. Reason number 1, it's man-made. Reason number 2, it actually lacks a crystal structure. Glass is a solid, but it's not a crystalline solid, okay? the atoms in glass are disordered. And by the way, glass has the same composition as quartz, SiO2, but quartz is crystalline, it has a crystal structure, glass does not. The atoms are all jumbled up, just in a mishmash. How about salt? Do you think salt is a crystal? Sure is, okay? Assuming it's not man-made and that it was naturally collected, maybe by people that, evaporate sea water or something like that, but no crystal structure, right? So let's look at some other things. Water, is that a mineral? No, because it's liquid. How about rock candy? No, because it wasn't formed by a geologic process. How about amber? A lot of people get fooled by this one, and it's kind of unfair because how would you know this? But amber is not a mineral. Kind of looks like a mineral, right? But is not a mineral because it does not have a crystal structure. Okay, it has a more of a amorphous glass-like structure. Okay, how about your teeth? No, because they were formed by a biologic process. Okay, so none of those things are minerals. Let's go on to the physical characteristics of minerals. Now I have 8 of them here, and there's actually more than that, but you just have to put 8. So you don't have to explain these, you just have to list them all out. But color is the first one. Now color is very tricky, and the reason I say it's very tricky is because if you take a look at your screen right now, you'll see lots of different kinds of quartz, but guess what? It's all quartz. Okay, so smoky quartz, citrine, amethyst, rose quartz, milky quartz, clear quartz. It's actually all the same mineral. It's just like little tiny impurities in it that cause the different colors. Okay, so color is, of course, every mineral has a color, but or some kind of way of defining its color. But that's not a very good diagnostic property. It doesn't help you identify it. Something that's a little bit more helpful is the streak. The streak of a mineral is the color of the pulverized mineral, so the powder. And the way that you test it is by rubbing it on a piece of porcelain. Okay, so you can see that this black hematite actually has a reddish brown streak. That's really helpful because some hematite is red, some hematite is black, but that always has the same color streak. So you can see how streak is a little bit more helpful. Mineral identification, takes time to learn all these things, but pyrite, for instance, has this beautiful brassy color. I showed you pictures of pyrite, right? Not only pictures, I showed you in the demo some pyrite, but pyrite has a black streak, so even though it's that brassy yellow color. Let's talk now about luster. Luster is how light reflects off of the surface. You can have different kinds of luster. You could have, for example, metallic luster, like pyrite does, and it looks metallic because it's kind of shiny and opaque. You can't see into the mineral, you can't see through it. It's solid, totally opaque, and the light reflects off of it in a real shiny way. Remember in the demo, you could actually see yourself in that beautiful pyrite crystal. Okay, it's so shiny. On the other hand, here's gypsum, has kind of like a sheen to it, right? So we call that silky or sometimes pearly. That's another kind of luster. Here's a whole bunch of different kinds. There's vitreous, which means glass-like, metallic, resinous means kind of like the luster of maybe like sap or syrup. That's the way that it looks. So it's lots of different kinds of luster. Here's beautiful examples of vitreous luster. Vitreous luster looks kind of glass-like, glassy. Here's some beautiful examples of metallic luster. By the way, if you ever wanted to know, the shiniest mineral, if you like shiny minerals, the shiniest mineral is something called cassiterite. And it's actually, what is it? It's actually tin. The elemental symbol for tin is Sn. Tin sulfide. I think it's SNS2 or something like that. But that's cassiterite. So you can look that up and see how shiny it is. Okay. The hardness, that's another very diagnostic characteristic. Very, very useful for us. So we characterize the hardness of minerals according to according to a scale of 1 through 10. 1 is the softest, 10 is the hardest. Talc is the softest mineral. Diamond is the hardest mineral. Okay. The reason I have a little baby here is because talc, you ever heard of talcum powder? Or baby powder? In the old days, they don't do this anymore because they found out it was mildly carcinogenic, but talcum powder is like, it's so soft they use it for baby powder, right? By the way, do you ever hear me? It's kind of funny. I'm listening to these videos, and sometimes you hear me rubbing my hands like this in the mic. It's like, oh, this doesn't sound very nice. I'm always rubbing my hands. It's so cold in here. This new building at Oso is so cold. It's like a meat freezer or something. Anyway, sorry, I just had to mention that. So anyway, here's your list of the Mohs hardness scale. So like I said, we classify hardness according to a scale of 1 through 10 called the Mohs hardness scale. Talc and graphite are the softest. Graphite, have you ever heard of that? That's your pencil lead. That's the stuff that's in your pencil that you're rubbing onto your paper, and it's so soft that it scratches onto your paper. Like your paper, you're not damaging your paper, right, when you write with it, because it's softer than the paper. So that's how soft graphite is. Then there's gypsum at number 2, calcite at number 3. That's the one that reacts with HCl, with any acid actually. Number 4 is fluorite. Number 5 is hilariously called apatite. The reason I say hilarious is because guess what your teeth are made out of? It's actually made out of, well, I guess it's formed by a biologic process. It's not a mineral, but it's basically the biological form of apatite. So your teeth are made of apatite. I just find that funny because, apatite, right? But has no connection to that other word of having a hearty appetite, right? Orthoclase is type of feldspar. That's number 6. Number 7 is quartz. Number 8 is the gem topaz. Number 9 is the gemstone corundum. Corundum is sapphire and ruby. And number 10 is, of course, diamond. Okay. So, specific gravity is another thing. It's actually better known as density. So we already talked a little bit about density in this class in the kind of beginning lectures. So galena, for example, is lead ore. Have any of you ever felt like a hunk of lead? And of course, if you fish, you might know that a lot of our sinkers are made of lead, right? Why is it made of lead? Well, lead is so dense, it gets to the bottom really fast, right? So lead has a high density because it has heavy lead atoms in it, okay? So that's the density. It's how much mass there is per unit of volume. So if you take a look, this is kind of cool. This is a picture of a very small ball that is made of a very dense metal. And this is a picture of also a very shiny ball that's much bigger in terms of volume, that's made of a very low density metal. And you can see that they are the same weight, right? So which one has the higher density? This smaller ball. Because you have, remember, it's the mass to weight ratio. This has a higher mass to weight ratio. How silly of me. Mass to volume ratio. This one has a much bigger mass to volume ratio because we have the same amount of mass contained in a smaller volume. Okay. So after that we have crystal habit. Crystal habit is the shape of the crystal that mineral likes to form. You saw in the beginning, I showed you a cubic pyrite, a lot like this one, okay? That cube is its mineral habit, its crystal habit. That's the shape that crystal likes to form. Mica likes to form these papery sheets. Some minerals like to form needles like that. Some of them like to form like these beautiful beryl. Ooh, isn't that a gorgeous gemstone? It's called aquamarine. It likes to form these kind of flat-topped prisms. And you can look at this, and some people might look at this and think it's quartz. Oh, but it's not quartz. Why? Because quartz likes to form those 6-pointed sides, right? That's more like what quartz looks like. So you can see how these are flat-topped. That's how you would know right away that's not quartz. That's something else. In this case, it's beryl, and it's because it's blue, we call it aquamarine. Okay, so quartz likes to form these points like that. Garnets like to form these things that kind of look like soccer balls. Halite likes to form these cubes. Diamond famously likes to form these what are called octahedrons. That has eight faces on them. So there's so many different things, really interesting shapes that are formed. And calcite likes to form these, what are called rhombohedrons, things like that. So once you kind of get more experience with the different shapes of the crystals, helps you identify them and figure out what they are. All right, number 7 is, I should have made this number 8, but that's okay. So specific properties. These are properties that are just kind of random, different properties. So, for example, calcite reacts with HCl, reacts with acid. Some things like magnetite are magnetic. Okay. Some things smell like sulfur. Some things taste salty like salt. I don't know. Sometimes I kind of wonder about this class, but it's obvious. Yeah. But salt is salty. So, but I guess the mineral name of that is halite, right? So that doesn't sound so obvious. Last property you should know is something called cleavage. So cleavage, what is cleavage? Cleavage is patterns to how the mineral breaks. Patterns to how the mineral breaks. And when a mineral has cleavage, it will break along these clean, flat planes. So do you see how this mineral has all these clean, flat planes, okay? So I want you to take a look at this picture. Look closely. This mineral sample that you're looking at has 3 planes of cleavage. I'm going to show them for you. So I'm going to show you the first plane, plane number 1. Okay? Plane number 1 is this. I'm going to write a 1. 1. 1. 1. 1. 1. 1. You see how all the 1, 1, 1. I could guess more. 1, 1. Okay? So that's cleavage plane number 1. Now, do you see how all those planes are all the same direction? They're different. There's like different surfaces, but they're all going in the same direction. Okay? So that's one cleavage plane. Only one cleavage plane. Now I'm going to draw cleavage plane number 2. 2, 2, 2, 2, 2, 2. Okay? That's cleavage plane number 2. Lots of different surfaces, all going in the same direction. Last one is number 3. I'll draw number 3. 3, 3, 3, 3, 3, 3. Hope you can see that. So 3, 3, 3. Okay, so that's cleavage plane number 3. So there are 3 cleavage planes there. It's a pattern to how the mineral likes to break. When you don't have cleavage planes, or when, you know, it just looks like, for example, I have so many things. Okay, well, I'll just explain it the other way. So, you know, minerals have this atomic structure, right? And sometimes certain bonds are easier to break than others. So, for example, mica, it's easy to break these bonds right here. And because it's easy to break those bonds, it splits easily into sheets. So this is cleavage, perfect cleavage in one direction, okay? So there's mica. You see how it splits into sheets, right? You all see that? Feldspar and pyroxene like to split into 2, kind of form this more kind of blocky look. See this? So here's cleavage plane number 1. Number 1. There's cleavage plane number 2. Okay, and so that's how. And some of these things kind of look even like there might be 3 cleavage planes. Okay, and maybe there are, but well, no, there's only 1. No, only 2. Sorry. Pyroxene, right? Pyroxene. Maybe that's number 1 and that's number 2. And maybe this one isn't a cleavage plane at all. Maybe this is 1 and this is 1 and maybe this is, I can't, it's kind of hard to tell looking at this. I can't really tell exactly, but feldspar only has 2 cleavage planes. Amphibole has 2 cleavage planes too, and I want you to see how similar pyroxene and amphibole look to each other, right? And the only way that you can tell the difference between them is that one has the angle between the cleavage planes. So pyroxene has cleavage planes that are like a 90-degree angle like that, and amphibole has cleavage planes that are more like tilted or slanted. So that's how you tell the difference between pyroxene and amphibole. So I'm going to kind of go through this stuff kind of fast because this is really important if you're taking the lab. I don't know if any of you are taking, I don't think any of you are taking the lab in my online class. So I'm going to kind of go through this stuff faster. But that's what 3 cleavage planes look like. See how it kind of splits into cubes for halite. And galena also has 4 cleavage planes. Sorry, 3 cleavage planes. See, cleavage plane number 1, cleavage plane number 2, cleavage plane number 3, right? This is cleavage plane number 1 there. This is number 3. This is number 2, etc. Okay, there's calcite. That's 3 cleavage planes, but not at 90-degree angles, so it kind of looks like tilted. And then you can have even 4 or 6 cleavage planes. So fluorite and sphalerite both give you different examples of how you could have 6 intersecting planes of cleavage. Pretty crazy, right? So anyway, when you have material like quartz or olivine, not all minerals break with cleavage. Some of them have no cleavage. Quartz and olivine have no cleavage. And when they break, they just break kind of randomly. Like, you know, like look at this cement. It looks like somebody took like a sledgehammer and hit this cement, right? There's no rhyme or reason to it. How many cleavage planes does this quartz crystal have? What do y'all think? The answer is 0. It has no cleavage planes. And you might be looking at this and be like, wait, what? Dr. Hurt, no. Look at this. 1 and 2 and 3 and 4 and 5. It has so many cleavage planes. 6 and 7 and 8. And those are all crystal faces. Sorry. So not every flat surface on a mineral is a cleavage plane. It can also have crystal faces, and those are all crystal faces. So you have to look at the broken parts of the crystal to determine cleavage. Remember, cleavage is how the mineral breaks. Okay, so match the minerals with the correct cleavage. Halite. This is 3 directions, or actually let's do it this way. 2 directions at 90 degrees. That goes to halite. 3 direction, oh, I'm sorry, blah, 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 blah. How do I go back? No, I made a boo-boo. I made a boo-boo, sorry, there. Okay, 2 directions at 90-degree angles. That would be plagioclase, feldspar, okay? 3 directions at 90-degree angles. That would be halite. 3 directions not at 90-degree angles. That's calcite. 1 direction, that's mica. 0 directions, no cleavage, that's quartz. Okay. All right, so thank you for bearing with me with cleavage. Did I answer all the questions on here? Most common mineral of the crust, haven't gotten to it yet. Number 4. Number 5, what very common mineral reacts with acid? I did talk about that actually. So that one is, go back here, that one is calcite. So there you can see the calcite reacting with acid. Okay. What else do we have? Let's see, we did number 6, 7, 8, 9. Oh yeah, good. So we just did number 10 too. I'm sorry, we kind of skipped number 4, huh? I forgot if I talked about that or not. Let me see. Well, I'll just tell you right now, number 4. What's the most common mineral of the crust? Feldspars. That's why I talk about feldspar a lot. It's the most common mineral of the crust. It's like the most common mineral that you've never heard of, right? Probably coming into this class, you might have heard of quartz and things like that, but feldspar is the most common. All right, describe the cleavage of the following minerals. We already did that. Number 11, which of these images shows a mineral atomic arrangement and which one shows a glass? So what you're going to be looking for here is which one looks more geometric. Okay, which one looks more ordered? And the way that you figure that out, number 11, the way that you figure that out is, the way you figure it out. The reason for that is that minerals, remember, are highly ordered. So they look very geometric, like geometric patterns. Things that don't look geometric are not going to be a mineral. Okay. Okay, now we're getting to the rest of these questions, number 12 on, okay? So let's go over some of the most important minerals of the crust that I want you to know about. So we're going to talk about these guys: quartz, feldspar, mica, olivine, amphibole, pyroxene, hematite, clay minerals, calcite. I already kind of introduced this. So again, it's going over what we learned last time in matter and materials, okay? So remember, what is the Earth's crust made of on maybe like a majority of it? It's made of these silicon tetrahedra, right? So again, number 12, you have to draw, guess what? Another silicon tetrahedron. So there it is. You can draw it. It's right up there. So draw it. Okay, you just have to copy that. Do I have you put the charges? Yes, I do. So remember, every oxygen has a charge of what? Has a charge of -2, -2, -2, -2. Every silicon, there's only one silicon, has a charge of +4. And if you add +4, -2, -2, -2, -2, you get a net charge of -4. Okay, so that silicon tetrahedron is going to bond with cations like iron, magnesium, calcium, sodium, potassium to form different minerals. Okay, so let's talk about quartz. You got to know a little bit about all these important minerals. Quartz. Quartz is a very common framework tectosilicate mineral. Remember we talked about silicate structures? Tecto framework silicates, that's where all of the silicate tetrahedra are touching and bound together, right? They share, every one of their corners is shared with another silicate tetrahedron. So every oxygen is a bridging oxygen. That means that every oxygen of every silicate tetrahedron is bound with another silicate tetrahedron, right? Every oxygen in it is a bridging oxygen. Means it has a bridge to the next silicate tetrahedron. That makes it very hard. It has a Mohs hardness of 7. It is hard to erode. It has no cleavage, but it has a very distinct conchoidal fracture. That is a conchoidal fracture. Conchoidal fracture comes from, you might know this word. I think it's a Spanish word. There's a Spanish word. I mean, it's Latin ultimately. But conch means shell, like a conch shell, right? So you can see that shape, the conchoidal fracture, kind of looks like a clam shell, right? That's why. So most beach sand is made of quartz. These are tectosilicate minerals. They're very hard to erode. So when you go to a beach, a lot of this is just quartz. And why is it quartz? It's because it's like one of the last things to erode and break down. Okay. So at a beach, there's a lot of tumbling and turning and gyrating, and that really highly erodes and weathers the mineral. And that's how you end up with just all you have left is quartz. That's why you have a lot of quartz at the beach. Very important mineral, feldspars. Okay, the feldspars. They are the most common mineral of the crust. That comes in 2 types. There's potassium feldspar and plagioclase. Potassium feldspar and plagioclase. And we're going to talk about the difference between those. So the most common mineral of the crust, they're framework silicates, just like quartz. They're hard, but not as hard as quartz. They chemically break down into clay. Okay, so clay minerals are formed by the chemical weathering of feldspar. Okay, even though I don't have a question about that, I would suggest just writing that down in your notes or writing that down in somewhere in your packet. To remind yourself, because it comes very important as we go on in the class. It has 2 cleavage planes, like I've mentioned before. Okay, albite and microcline are 2 types of potassium feldspar. Okay, some potassium feldspar has these kind of wavy lines. That's called X-solution laminae, and that's how you'll identify potassium feldspar. Okay, so another type of feldspar is called plagioclase feldspar. Plagioclase feldspar, there's some really interesting types. There's albite, there's this labradorite. You might know labradorite, it's so beautiful. Gosh, I wish that you were here in the lab with me because I have a beautiful sample of labradorite. I forget if I showed you. I don't think I did show you in the demo. Maybe I should show you the next time. It's so beautiful, so awesome, and it's just sparkly blue, and it's really interesting. I'll have to show you in another demo. And there's biotinite. There's all these different types of plagioclase. So plagioclase contains calcium, but no sodium, while potassium feldspar has potassium, but no calcium. Okay, so the essential difference is whether it has potassium or whether it has calcium. If it is a calcium-bearing one, we call that a plagioclase. If it's a potassium-bearing one, we call it, guess what, potassium feldspar. Okay, that's the difference between the 2. Okay, another important mineral is mica. Micas are sheet silicates. They're soft and easy to erode. They have one direction of cleavage. And remember that now see how we're moving down the line of silicate interconnectedness. So we did the tectosilicates, quartz, and feldspars. Now we're going to the sheet silicates. We have 2 flavors of mica. We have muscovite, which is white mica, and we have biotite, which is black mica. We have amphibole. Again, now we're going down the list of silicate interconnectedness, and we get to amphibole. So amphibole has the double chain structure. Okay, so it chemically breaks down very easily, has two directions of cleavage. There's some pictures of amphibole. Here's some pictures of pyroxene. Remember, look how similar pyroxene and amphibole look, right? Very, very similar in hand sample. How do you tell the difference? Pyroxene has cleavage planes that are at almost 90-degree angles, whereas amphibole does not. Okay, oops, how did this happen to me? I'm getting so confused. I went like to the end. This has cleavage planes that are at less than 90-degree angles. Okay. All right, olivine is the last in terms of silicate interconnectedness. See how none of the silicates touch. Okay, those are isolated silicate structure. It has no cleavage. Chemically, it breaks down like that, right? That was a crummy snap. I'm sorry. Just don't have it today. Okay, so olivine breaks down very, very easily. So that's why something like this, a beautiful green sand beach that you can find in Hawaii, very, very rare, right? And you're probably looking at this like, whoa, wow, I didn't know that. It's very rare. Why is it very rare? Olivine breaks down very easily. And so that's why it's pretty rare to have an olivine sand beach. Okay, so why does olivine break down so easily? Silicate structure, right? It has an isolated silicate structure. Those silicate molecules are not connected to each other. All right, on to calcite. Calcite is kind of different than all of the other things we talked about. Notice how everything we talked about so far is a silicate. Calcite is not a silicate. Notice how calcite has no silica in it. It is not a silicate, it is a carbonate. It has this little bugger, which is a carbonate molecule. This is a carbon in the center. These are oxygens. Okay. Calcite is so important because marine organisms make their shells out of calcite. So that ultimately gets preserved in the rocks, and that's how you get limestones. So limestones are made out of calcite that's usually biogenic in origin. That means it was created by some kind of marine organism. And you're probably sitting there and thinking, but doctor, you just said that minerals don't form from biologic... Obviously, whoever came up with all these things was not a philosopher. So I don't know. It's full of little inconsistencies like that. But anyway, one of the other minerals I'd like you to know, hematite. Hematite is, you ever see red soils like this? There are a lot of them in like Oklahoma, Arkansas, Kansas. This comes from the breakdown of iron-bearing minerals and creates iron oxide, which is just rust. All hematite is rust. Hematite is the mineral form of rust, iron oxide. Okay. So many of these iron-bearing minerals like pyroxene, olivine, amphibole, when they weather and break down chemically, they create hematite. Okay. So just like clay is a weathering product of feldspar, hematite is a weathering product of things like iron-bearing minerals like olivine and amphibole and pyroxene. Speaking of clay minerals, we have a lot of clay here in Texas. See, any of you live in a house with foundation problems? It's because of the clay. So clay minerals are formed by the breakdown of feldspar. Some common ones are kaolinite, bentonite, montmorillonite, and they compose the rock called shale. So someday when Texas, I don't know, gets buried, all the clay soil is going to form a rock called shale. Okay, we'll talk about more about that when we talk about sedimentary rocks. Clay minerals, if you actually zoomed in with a really powerful microscope, you would see that clay minerals are flat and platy. That's how they look. See how they look like all these little sheets? They almost look like mica. That's actually the structure of clay minerals. They're very flat, and that's why when you look at shale, do you see how shale kind of looks flat and platy like that? It's because that's the flat and platy atomic structure of the clay minerals that compose it. Clay minerals, like I said, are composed, or they come from the weathering of potassium feldspar. Hint, hint, number 15. What is one example of a non-silicate mineral that's common in the crust? Well, you could put a few things. Calcite and hematite both are non-silicate minerals, right? It's a carbonate, the other one, hematite's an oxide. Okay, so that's it. In summary, minerals are naturally occurring, solid, formed by geologic processes. Minerals have a crystal structure. They have a definable chemical composition. You have to be able to write a chemical formula for it. There's examples of crystal patterns. They have a crystal structure, means it has a repeating pattern to its atomic makeup. They're the building blocks of rocks. They form from either crystallization of a melt, precipitation from a fluid, mineralization, growth at high pressures, or freezing from gases. They have some characteristics such as color, streak, hardness, crystal habit, luster, density, and cleavage. That's how you identify them. Silicate minerals are the most important and most common class of minerals on Earth. They are classified by the degree of interconnectedness of the silicate tetrahedra. Okay, there are the isolated silicates like olivine. There's the, I don't talk about bow ties or rings, but there's the single chain, which is pyroxene, the double chains, which are amphibole, the sheet silicates, which are the micas, and the framework silicates, which are all quartz and feldspar. Okay, calcite and hematite are common non-silicate minerals in our crust. So here's some good examples of exam questions. You can kind of test yourself. What is a mineral? Make sure you know the 5 criteria that define a mineral. How do minerals form? Make sure you know the 5 ways that minerals form, right? That's freezing from a gas, growth at high pressure, biomineralization or mineralization, precipitation from a fluid or evaporation, and crystallization. Okay. What are silicate minerals? Just minerals that contain the silicate tetrahedra, that's all. Okay. Can you be a silicate mineral and have no silicon? Nope, sorry. You have to have silicon to be a silicate mineral. What are the different silicate structures? The different silicate structures are isolated. That means that the silicate tetrahedra do not touch. Single chain. That means that every silicate tetrahedron is connected at 2 points. Double chain. That means that every silicate tetrahedron is either connected at 3 points or 2 points. Sheet. Every silicate tetrahedron is connected at 3 points. Or framework. All silicate tetrahedron point, they're connected at all 4 points. So every oxygen is a bridging oxygen. Okay. What are some common non-silicate minerals? Calcite and hematite. Okay. So those are all examples of test questions you could have. Here's some like multiple choice form that you could possibly come up with. So which of the following is not true about minerals? All minerals are compounds of more than one chemical element. That's not true. Copper, gold, diamond, graphite, silver, iron, all those things are minerals, but they're only composed of one element. Which of the following minerals is hardest? Quartz. Which of the following mineral fizzes with contact with acid? Calcite. Okay. So those are definitely questions that are on your test. The way your tests are is that you get a bank of questions and it randomly draws. So I can't like guarantee you're going to have those questions, but I can guarantee you that, well, I guess technically I can't guarantee you that somebody will have them. I guess it could have extreme random possibility, but most likely somebody will get those. But anyway, that's all I have for you today. Kind of a long lecture, huh? So anyway, I'm going to stop here and hope you have a good rest of your week. And if you have any questions whatsoever, please contact me and I'll do my best to help you. So I'll leave you here now. Have a good time, good week, and talk to you next time.